Okay, so my name is Pedro. I work at Fairgate Labs. We are part of BitBMX Force. It's components about Fairgate, input, output, and rootstock. And the idea is to push BitBMX as a solution of choice for disputable computing on Bitcoin. What we'll be talking today is about how to use BitBMX on a hands-down approach, so you get an idea of the modules that you will be using and how to interact with BitBMX. We will also be talking a bit about the workshop today, the bitcoin++, as we have some prizes in it. So, what is BitBMX? Bitcoin scripts have several limitations. There aren't enough opcodes, it's not Turing complete, you cannot do complex computation, and there is, in the foreseeable future, no changes to these opcodes or the way Bitcoin script will work. BitBMX tries to solve that, allowing complex computation off-chain and then a dispute based on-chain of the result of that computation. Two parties agree on a program that will be run by BitBMX, and the result will define how the locked transaction, the locked funds will result. Where are they going to be sent? This is all done by BitBMX protocols, which are a graph of Bitcoin transactions that sets the logic on how it will operate and manage the result of the computation being done. Any program compiled into a RISC-V binary should work as an output of the program. For example, we usually use zero knowledge proof Groth16 verifier, but could be others. And the way it works is an optimistic protocol. If everybody agrees on the result of the computation, it's a happy path, then nothing happens. It's a very small footprint on chain, so it's very cheap. If somebody disagrees on the result of the computation, then it's an on-chain dispute. It takes several transactions to be resolved, but it's not that expensive. So, let's go to some examples. We have some applications using BitBMX. One of them is the Union Bridge in rootstock. It's a decentralized bridge between rootstock and Bitcoin, allowing to move BTC to RBTC and the other way around. Rootstock is an L2 blockchain from Bitcoin. It has a one participant honest assumption, that is that the protocol will work as long as there are at least one honest participant. This is great compared to the previous way of doing things, where you need at least half plus one of the participants. So the requirements for liveness and decentralization are way better, right? This is why we talk about trust minimized bridge, because you only require one participant to be honest for the whole thing to still work. On the other side, we have the Cardinal application, which allows us to move ordinals from Bitcoin to Cardano. These ordinals are considered like NFTs for Bitcoin. So this was a major milestone for us. Again, we have at least one participant to be honest, which is just minimized bridge. That is great again. And it allows us to lock ordinals on Bitcoin and have them on Cardano, so we can trade it whatever we want or do what we want those NFTs on Cardano. We use the transfer of ownership protocol that was created by Fairgate, to reduce the need of operator collateral. We have a paper about this and more information on our Knowledge Hub, so feel free to go there if you want more information about that. BitBMX is not yet on mainnet. It's not productive ready. We're undergoing several security audits and whatnot. But these applications are live on testnet. They are on closed alpha, but still working examples, so we're very proud of them. As for the hackathon that we'll be conducting today, probably why most of you are seeing this talk, we have a 2 million SAT prize, which is pretty nice. The judges primarily will select the winners by 3 points: routine difficulty, which is the idea in general, innovation, project impact, ambition, the routine execution, that is achievement, code, how was it built, engineering side of stuff, right? And the general effect, the wow factor, how mind-blowing it is, or how good it is for marketing to sell it. But yeah, that thing that pops the eye. Okay, so what can I do for the hackathon? BitBMX, as we mentioned before, allows you to create optimistic protocols on Bitcoin, right? Performing computation off-chain and use Bitcoin L1 in case of fraud, proof, and settlement. So it pretty much lets you do whatever computation you want, but some of the cases that may be like more important, I mean, bring whatever you want to the table. I don't want you to be biased by this. This is just examples. Cross-chain bridges, as you see, for example, the Union Bridge and Cardinal are examples of this. BitBMX verifies the logic between Bitcoin and other blockchains, and you can do trust minimize the things with them. So bridges are like our number one thing, probably. Also, we have stablecoins and decentralized derivatives, where BitBMX manage the collateral liquidation logic. If that stablecoin moves out of its peg or whatever, you can enforce rules over the collateral made and computation be done off-chain. Also, you can enforce mint and redeem rules to it. We have also verifiable games. Any game you want can be made out with BitBMX. There is an example in Python from Pokemon, if I recall correctly, by Rusto Labs. So that's fair game as well. No pun intended. And the idea is that you set the game logic into a program, and wherever you want it, that some player says, hey, he didn't do that. For example, I don't know, chess, and you say you move your queen to a5 or something like that. But the other player said, hey, he didn't move there, he moved in another direction. Both present proof of the computation made, and they have to set collateral previous to the program. Whoever is cheating loses that money. If not, the game resumes as expected, and the actual winner wins. Again, similar to games, you have tournaments and betting, where a system settles the BTC without trusted intermediaries, which is a big step on decentralization, as you don't need a third party to hold that collateral. Sorry. For the hackathon, we have an example app. You can find it in our repository at Fairgate Labs. It's called BitBMX Hackathon Game. It includes a backend and a frontend. It also scripts to run the whole BitBMX suite, so you can test it out of the box directly and interact with it, get an idea on what it does, how it works, and how you could use it to your own project. It also has the documentation on READMEs in several parts of the project. And you can always contact us on Telegram. at BitBMX devs. We will be happy to answer your questions. Also, you can learn more about BitBMX at our Knowledge Hub. It's in Fairgate Live's page. You can go there to Knowledge Hub. We have several slides, papers, videos, and a lot of more information about the different protocols that BitBMX has and BitBMX itself. So let's go to something more practical on how do we actually use BitBMX on a developer perspective. Okay. First things first, we need to communicate with BitBMX. The way of doing that is using the message broker. The link there goes to our repository, again in Fairgate Lab GitHub, where it's called BitBMX broker. It's a RPC implementation. RPC sends RPC messages for Rust. Most of the things written for BitBMX are in Rust, so that's our primary coding language. What we do with this is we send message to BitBMX client. Internally, BitBMX also uses the message broker to send these messages to the different components that it has. But we will primarily use to interact with BitBMX client, as it's the one that coordinates with the other components. It's TLS encrypted, so it's secure and encrypted end-to-end. It has certificates for both client and server, and allow list and routing. So it will only connect to those. It will only connect to whatever we say it will connect. This is important, especially for when we're trying to create the participants. Each participant has to know each other, so you will need to know the IP that they will be connecting to. Also, for our application, they will need to know what instance of BitBMX are they connecting and where that is, and BitBMX has to have our application in the allow list. This is mostly for security reasons. So a brief code example. Here we're going to initialize the broker. We're going to start our configuration. You can find that in config YAML. This is also in the example repo, but in mostly any repository of BitBMX that uses the broker, you will see this config file with IP, port, certificates, and previous things that we mentioned. We will be creating our broker. In this case, we will use a dual channel. Dual channel is because it accepts to send message and receives them, but the actual server that will be listening is the BitBMX client. So with the broker config, our application has an ID which is called L2 ID. This is an internal from BitBMX, as it considers other applications as part of the L2. But as you can see, it's pretty straightforward. And then how we send a message is through the incoming API BitBMX API messages. This is a class that has all of the type of message that you can send to BitBMX. So it's what you will be using. In this case, I'm getting a public key out of BitBMX. I just need to send the ID, and the value is if true or not. If it's not created already, it creates it. But as you can see, it's pretty straightforward. So you mostly need to pay a lot of attention to the incoming BitBMX API message, which is in BitBMX client types. And the result that you will be getting is an outgoing BitBMX API message. As we were saying, all of our messages will be going directly to the BitBMX client, which will be the one that's coordinating stuff. What is BitBMX client? It's where the protocols live. It's where we need to add them new ones. By default, we already have a dispute protocol that exists there, and you can see in examples the Union Bridge and Cardano. These when I mean you can see them, is inside the code in our Fairgate Labs repository at GitHub in bitbmx client. So we uses bitbmx client uses the CPU to verify the program execution through bitbmx show dispatcher. So we have the protocol and the execution of the program going through the bitbmx client, as well as the connection with other operators who will also be running their own bitbmx clients instance, and the track and dispatch of transactions to the Bitcoin network. We react to specific transactions, which allows to collaborate with valid fluxes set up by the protocol, and also it automatically challenges malicious activity. So if for some reason bitbmx detects that it's doing something that's out of the protocol, or if a challenge transaction is detected, it will react automatically. When I mean react automatically is the protocol have this graph of transactions on Bitcoin that we will see later on, and if he detects that a challenge is taking place, he will put the signature on some pre-established transaction for that protocol so it can continue. So how does setting up a protocol and code a program and a protocol? This is a small code example. So we will talk about program and protocol later on, but I want to show this first because the others are way more complex. This is like a good starting point. The program, that will be the computation that we're gonna be running when we do the disputable computation part that we mentioned before, is a RISC-V compiled. In this case, it's RISC-V 32, and it's a YAML. We'll later on see why it's a YAML. We'll need the path to that program, and we will also need the ID. Most IDs on bitbmx are UID, and you will have to handle those all in your application. bitbmx, it's kind of transparent about that. It doesn't store that information, so make sure whenever you're creating a program, the participants, public keys or whatnot, to hold those IDs on your application. So in this case, I'm setting which program we're gonna use, the path of it, and we're gonna send that information to bitbmx client, and then we're gonna set up the program. The set bar that you're seeing message here, it allows us to add inputs to the program and to the protocols. So when we're gonna execute down here, the setup, which is done with the message setup, we need to already have set all of the variables needed for the protocol or program inputs in order to be run. In the setup, we say which program we're gonna do with the program ID. Program ID points to all of the information needed for the program. Program type, in this case, is dispute resolution program. That's why program type DRP. And then the address of the participants. The address is actually IP port and the certificate that gives you an identifier for that participant. Once we have that, we will send this to the bitbmx client. Now, when we do this, we only set up for ourselves. In order for this to complete, each participant has to call with the same message on their bitbmx node, and they will interact automatically, setting up the protocols when all signatures have occurred. If not all participants have done this, then the setup is not completed, because it means that not all participants agreed on that protocol/program, right? So this is how you make sure that everybody says, okay, we're gonna run this computation that's come from this program And this is the people involved. Now, in the heart of all, we got the BitBMX CPU. This is one of the most important parts of BitBMX, as it's the one that will run the program. It maps every RISC-V instruction into a Bitcoin script. This is also measured because Bitcoin script does not implement all opcodes, so a lot of work and conversions need to be done in order to do this. Why do we need to map every single instruction? Because in case of dispute, we need to prove which instruction was not correct if somebody is tampering on it. The evaluation of the program is done off-chain. Most of them will be zero-knowledge proof, and they are very CPU consuming, and a lot of computation is required. That's why we do it off-chain. And dispute logic to identify the faulty instruction in case of challenge is done with an NRE search. We track every instruction, and then when the dispute started, both parties need to show their code. If they wanted to add all, it would be way too much to put it on chain. So what we do is, instead of a binary, we do an NRE search. Currently, most of our programs are using like 8 divisions to try to find where is that the divergency started and the faulty line. Trying to find that, we will find who is the one that is not getting that truthfully result, and thus ending the dispute in who wins it. The CPU runs in a separate process inside the BitBMX show dispatcher to allow potential parallel multiple executions. Again, this is really consuming, so you may want it to run this particular thing in another platform on another machine, but the rest of the BitBMX solution is in something like way cheaper. So, what does a program look like? This is a very small program. Programs need to be in C++ or Rust at the moment. This is in C++. It's a program that checks for the sum of two inputs. So we have 3 inputs. The first one is A, the second one is B, the third one is C. Input A and B, sum needs to give C. Otherwise, the program will fail. Again, this is a very simple example, but so you can get the idea. We need to build a program into a RISC-V. We're currently using RISC-V 32 to create a .elf file. That is what we will be using on BitBMX. We have a couple of helpers to give you a head start on this. So you can use it. It's BitBMX Docker RISC-V 32 in our Fairgate labs. There it has a Docker image where you can just put the code and it will build it and create the ELF. It helps a lot. We have one for each operating system. You know, we have for Mac, Linux, Unix, and once you got that, you can compile your program and get the ELF. What you will probably be using is not the program itself, but a zero-knowledge proof with a ELF16 verifier. Again, this helper allows you to create that. You will have to create the verifier and then compile it. The YAML that I was previously talking to you about has these things that we need to set up. Mostly are input for what program will be, that is the ELF file. Instructions about the NRE search. This is how much power you set up and how many divisions you want. More divisions means it's quicker, but it also means it will need more CPU to use it, and it will probably take more chances on chain. The max number of steps is how many of these energy search will be conducted at max. This is a very small value because it's an example program. For zero knowledge proof, they have a bunch more of zeros, so you can check that again in the examples in BitBMX client. But again, this is very small because it's a really simple program. Then you have the inputs. In this case, the input is considering two parts. The first part being constant 8 size, which is actually 4 bytes from the A input and 4 bytes from the B input. And the C input will be the other 4 bytes that you will see that says owner proof and the previous owner const. This is because in the example app for the hackathon that we made, you set up a sum of two numbers, let's say 1 and 2. Both agree that the program is the setup of two numbers, 1 and 2. That's why it's a constant. Well, every participant agreed on that when setting up the program. And then the prover needs to say, okay, what is the number that gives that sum? And so the prover needs to add that later on chain as the proof. And it's what it's going to be executed by the program. Okay, so as Palpatine here, we need somebody to execute that program, and the one that is handling the execution is the CPU, but the one who ordered it is the protocol. Protocols are like plugins for BitBMX, and they add extra functionality. This is probably what you will be designing. Programs are big and complicated, so we're not expecting you to finish this on the hackathon, but it's a good idea that you understand what they are, what they do, and how they are built. So protocols set the flux using Bitcoin transactions. They set all of the flux is set by using the Bitcoin transactions into a directed acyclic graph. It's directed because it only goes in one sense and has no cycles. That's why it's acyclic. Protocols also store and read information from the set bar that we made previously. So each time we set a bar, we are storing information into the protocol. They send the transactions and receive the updates about them. This is done automatically, so BitBMX client has the power of sending transactions and listening to them to understand if they they were sent on chain, they need to be speed up, or they were cancelled or written. We sign the transactions with the key manager, or if it's in the case of a multisig with multiple participants, we use music too. We also can sign one-time signatures using Winternits. Sergio is going to be doing a talk about payment channels that he will be mentioning how to work with one-time signatures. So if you want to add that to the hackathon, that will be also counted as using a part of Fairgate. And protocols hold the program information. As we see, when you set up the protocol, you indicate the YAML that we'll use with the ELF definition. So how a protocol looks like? Well, this is actually a small part of a protocol. Each one of the arrows is a Bitcoin transaction. You can see that multiple arrows come from one single point. This is because those are taproot transactions. So you consider each one of the boxes like a part on the flow, but each one of the small squares there is an expended transaction output from Bitcoin, and its corresponding input in the other part. So you kind of design the flow of the program just using Bitcoin transactions. And well, it's hard work. Mostly you have to always check out for timeouts in case one participant does not respond in time or refuses to answer. You have to you have to sign the transactions, but also there are some pre-signed transactions when setting up the protocol. So we all agree on something, then we all sign it, but don't send it automatically on chain, but we send it when something of this happens. So it's complex. I won't deny that. Okay, so as C3PO here, it can get a bit scary, but we have helpers for this. So BitBMX created the protocol handler and later on the protocol builder to help us use that. Let's start with the protocol handler. In order to add a protocol to BitBMX, you will need to implement the protocol handler class. Whenever you want to add a protocol, you need to add it in source program protocols. There's like where all protocols live inside BitBMX client, and it needs to implement the handler. It has several functions already built in, but some that you will need to implement, like the generate keys, define protocol setup, receive transaction news, and trigger transactions on finish. Generate keys is only like a hook when you are creating the keys for the whole participants that we will call the aggregated key. And you want to hook to that instance and perform some code there. That's where you're going to add it. The define protocol setup is similar to the previous one, but to the setup message. So when you receive a setup message for your protocol, it will call to that function directly. Then the receive transaction news is all transactions in the protocol will have names and belonging to your protocol. When BitBMX detects that one of those transactions was sent, it will inform you, and that's the hook where you will be able to code out whatever you want. And finally, the trigger transactions on finish is once setup of the protocol is complete, or some of the other actions were to trigger a particular transaction after that. And then we have the protocol builder. The protocol builder is what helps you out to create the graph that we saw earlier. It allows you to create complex protocol diagrams using Bitcoin transactions. It creates and stores all of the Bitcoin transactions that we saw early on. They can be set with Taproot. We do not accept legacy transaction because of the cost, but you can do pretty much whatever you want inside those transactions. We store metadata about the inputs and outputs, spending path and signatures, so the protocol can later on retrieve a particular transaction at the moment, perform checks on that. We can add speedups using child pays for parent transactions. Why do we use that and not replaced by fees? Well, as some of the transactions are pre-signed, we need to speed them up without changing them. Otherwise, we will need all of the participants to sign them again. So that's why we're using child pays for parent. Also, Protocol Builder helps you out to distinguish dust and transaction fee calculation. I know that this doesn't mean much, but when you're working with several transactions connected to each other, can be a real pain to estimate the transaction fee or the final amount that you will get after deducting all of those dust and transaction fees. And last but not least, the graph visualization. It allows us to see the graph that we have created with the protocol builder in a visual manner, which helps a lot to understand what we're doing or what we're doing wrong if debugging. Let's see some code example of the protocol builder. Here we are creating a verification of an aggregated key. The aggregated here was not added because it will be too long, but it's the aggregated key created using music2. This will be the public key at this moment. And we create a script that it checks for it to see that if the message was signed with that public key of the aggregated signature. And then we create a time lock that will use the public key of the aggregated and a certain number of locks. The sign mode aggregated that you see here is a helper. This will tell BitBMX that all of the participants need to sign it. So it will talk peer-to-peer with all of the other participants saying, hey, I have this message that I need to sign, and the other ones will sign it. Finally, we create the output type of, in this case it will be a taproot, put the amount that we want to send, the public key that will be sending it, and the scripts that will be part of it. In this case, it could be signed by everybody or a timeout. Once we have the output, what we're going to do is to add it to our protocol. And this allows us to just create a very small output transaction. And what you do is you keep adding transactions, creating outputs and inputs, and in that way creating the whole protocol. At the end, you just kind of do protocol build, and it will check that all of the transactions are correct, and it will give you the Bitcoin transactions. In summary, we have three big pieces: BitBMX CPU. Also, you will need the dispatcher with that, but the CPU is like the most important part that runs a program. The program needs code that is created in C++ or Rust. It will usually be a zero-knowledge proof in RISC-0. You compile it with RISC-V 32. You can use the Docker helpers that we have on our repository, and you create a YAML file that has all of the information for the program and the inputs and NRI search. Then you have the BitBMX client, where you create your protocol. You need to implement the protocol handler. You need to create a cyclic graph using the protocol builder, and you need to add it to BitBMX client. Now we have our protocol and our program. We're ready to use it in our app. What your app will need to do is set the variables using setvar for the inputs, and then set the message to set a program to actually set it up and start the whole thing. I know that it seems like a lot, so nothing. Let the BitBMX force be with you. And thank you for hearing this out. Okay, any questions? If you need, we will try to upload this video and also send links on the slide. We'll be around if you want to talk to us, and I'll be here these 3 days, so feel free to contact me or talk to me or whatever. Thank you.